Welcome to this explainer. Today we're diving straight into one of the most dramatic, high-stakes battles happening anywhere in the universe. And it's a war fought not with weapons, but with the fundamental forces of nature itself. Deep inside a dying star, there's this ultimate cosmic tug-of-war going on. On one side, you've got the crushing, relentless, inward pull of gravity, and on the other, the bizarre, completely invisible shield of quantum mechanics. So who wins? Well, the answer to that question dictates the fate of stars, the creation of black holes, and literally our entire ability to measure the size of the universe.
Now, to really wrap our heads around this battle, we first have to look at the battlefield itself, a white dwarf star. When a star like our Sun finally dies, it leaves behind a core that's roughly the size of the Earth. But hey, don't let the size fool you. A typical white dwarf is an astonishing 200,000 times denser than our planet. I mean, just picture that. A single teaspoon of this material would weigh tons. That makes white dwarfs some of the absolute densest collections of matter in the universe, really only surpassed by extreme objects like neutron stars and black holes.
Section 1. The Fate of our Sun. Okay, let's dive into this and see exactly how a star reaches this extreme, compacted state. Every single second of its life, a healthy star is locked in this delicate balancing act. Normally, a star supports its own immense weight through nuclear fusion. Deep down in its core, atoms are constantly smashing together, releasing tremendous amounts of energy. And this creates an outward internal pressure that perfectly balances out the inward crush of gravity. But eventually, the fuel runs dry. Fusion stops, and without that outward pressure, gravity just takes over. It mercilessly compacts the star's matter inward, smashing the very atoms together until it feels like the whole star should just collapse entirely into nothingness. But it doesn't. And the reason it survives brings us to one of the most fascinating phenomena in all of modern physics.
Section 2. The Quantum Shield. So, what saves the star? It's rescued by a fundamental rule of quantum mechanics known as the Pauli exclusion principle. Simply put, this principle states that identical particles, like electrons, are strictly forbidden from occupying the exact same energy state or physical space at the same time. Now, in a normal gas, there's plenty of room to move around. But in a dying star that's being violently compacted by gravity, the density is so extreme that the electrons are crushed right up against each other. All the available slots are taken. The matter turns into what physicists call a degenerate gas. Gravity desperately wants to compress the star even further, but to do that, it would have to force electrons into spaces they are quantum mechanically forbidden from entering.
Because gravity is squeezing everything into such a ridiculously tight space, those electrons just can't occupy the same state. So to avoid violating Pauli's rule, the electrons are forced into higher and higher energy levels. They get pushed into extreme velocity positions. They start zipping around incredibly fast, not because they're hot, but because they literally have nowhere else to go.
Let's walk through how this actually builds up into a physical shield. It's basically a logical chain reaction. First, the density rises under the crush of gravity. Second, the average distance between the electrons shrinks down. Third, thanks to Heisenberg's uncertainty principle, as their physical positions become more strictly defined, their momentum absolutely has to grow. And finally, all this extreme electron velocity creates a massive outward physical force. This is what we call electron degeneracy pressure. It's the invisible quantum shield that holds the white dwarf up against the crushing weight of its own gravity.
What's absolutely wild about this degeneracy pressure is that it is completely independent of temperature. Normal gas pressure, like the air inside a helium balloon, drops if you cool it down. But you could theoretically freeze a white dwarf down to absolute zero, and this quantum pressure would still be right there, stubbornly holding off gravity.
Section 3. The Chandrasekhar Limit. But is this quantum shield totally invincible? Well, for a long time, physicists honestly weren't sure. It took a truly brilliant young mind to realize that this shield actually has a breaking point. Picture this. It's July 1930. A 19-year-old Indian student named Subramanian Chandrasekhar gets on a boat bound for Cambridge, England, to start his graduate studies. And during this long sea voyage, he doesn't just kick back and relax. He actually works out a fundamental limit of the universe. Chandrasekhar realized that the current models of white dwarfs were missing one absolutely crucial ingredient: Albert Einstein's theory of special relativity.
You see, degenerate matter has a totally counterintuitive quirk. As you add more mass to a white dwarf, it doesn't get bigger. It actually shrinks. It's crazy, right? More mass means more gravity, which means the electrons have to squeeze even closer together to generate enough outward pressure to hold the star up.
But there's a cosmic speed limit.
As the star shrinks and gets denser, the electrons are forced to move faster and faster until their velocities start approaching the speed of light, and that is where special relativity takes over. In a normal, non-relativistic state, the pressure is proportional to the density to the power of 5/3. But as those electrons become highly relativistic, the equation of state essentially softens. It becomes proportional to density to the power of 4/3. At that specific threshold, the degeneracy pressure is simply no longer stiff enough to stabilize the star. Gravity wins.
So the crucial takeaway here is this specific number, approximately 1.4 times the mass of our Sun. That right there is the Chandrasekhar limit. If a white dwarf's mass stays below this line, it lives on peacefully as a stable, cooling remnant. But if it approaches or crosses that 1.4 solar mass threshold, the quantum shield completely fails.
Section 4. When the limit breaks.
And when that limit breaks, the cosmic consequences are absolutely catastrophic. If the white dwarf is forced over the edge, say by siphoning off mass from a nearby companion star, the gravity becomes so overwhelming that it literally crushes the electrons directly into the protons. Through a process called inverse beta decay, they merge together to become neutrons. In a fraction of a single second, the entire Earth-sized star collapses into a superdense sphere just a few miles across. It becomes a neutron star, supported now by the degeneracy pressure of neutrons instead of electrons.
Alternatively, if we're dealing with a white dwarf made of carbon and oxygen, approaching that 1.4 mass limit triggers something else entirely. The immense density and temperature can ignite a runaway nuclear fusion reaction. Because the star is degenerate, it can't just expand to cool itself off like a normal star would. The carbon fusion rapidly spreads, and the entire white dwarf detonates in a colossal thermonuclear explosion. We know this event as a Type Ia supernova.
Now, because these Type Ia supernovae always trigger right when a white dwarf hits this exact uniform mass limit, the resulting explosions are remarkably consistent in their brightness. It's like having a 100-watt light bulb shining across the universe. Astronomers call them standard candles. By observing just how bright these explosions appear from Earth, we can measure immense cosmic distances. In fact, this is exactly how we figured out that the expansion of our universe is accelerating.
Section 5. Super Chandrasekhar exceptions.
But science is always evolving. Recently, astronomers have spotted some peculiar Type 1a supernova that are simply, too bright. They're overluminous, which strongly suggests that the white dwarfs that exploded must have somehow been significantly heavier than that strict 1.4 solar mass rule. This completely sent theoretical physicists back to the drawing board, and brand new models are now suggesting that under very specific extreme conditions, the absolute mass limit could actually be pushed much higher, potentially all the way up to 4.68 solar masses.
So how on earth is that possible? Researchers have tossed out a few really fascinating ideas. One is the presence of intense internal magnetic fields. These super strong fields could provide extra internal pressure to help prop the star up against gravity, artificially raising its maximum mass. Another, far more exotic theory relies on something called dynamical non-commutivity. Basically, it's a complex quantum effect that fundamentally alters how momentum variables interact at extreme densities, massively enhancing the star's carrying capacity. So while the standard 1.4 Chandrasekhar limit remains a foundational pillar of astrophysics, these super Chandrasekhar models just prove that the universe always has a few surprises left up its sleeve.
Section 6. Physics' Ultimate Intersection.
Ultimately, what makes the Chandrasekhar limit so breathtaking isn't just that it dictates the dramatic death of stars, it's what it represents for human understanding. This single astrophysical phenomenon beautifully unites the three most foundational pillars of physics. Think about it. You have quantum mechanics supplying the Pauli shield, special relativity setting the absolute cosmic speed limit for the electrons, and classical gravity providing the crushing downward force. They all intersect right there, in the heart of a dying star. As physicist David Tong points out, while white dwarfs don't quite reach the ultimate extremes of the Planck scale, their physics points us directly toward the holy grail of modern science. Because the gravity in a white dwarf behaves classically, but the matter resisting it behaves entirely quantum mechanically. Studying these objects pushes us right to the very boundary of quantum gravity. It's the quest to quantize spacetime itself.
Subrahmanyan Chandrasekhar was just 19 years old when he realized that combining relativity and quantum mechanics would put a hard physical limit on the mass of a star. Today, nearly a century later, we are still using his limit to measure the universe, and we're still grappling with the extremes it creates. So I'll leave you with this thought. If the sheer crushing weight of gravity, the invisible shields of quantum mechanics, and the strict speed limits of relativity all converge to dictate the explosive death of stars,
what other mind-bending phenomena are just waiting to be found out there at their intersection?